Here we go. All right. First off, the second law of thermo, we've already stated this, but just to like explicitly give it a name, uh, heat naturally flows from hot to cold. Heat naturally flows from hot to cold. That's the second law of thermodynamics. Okay. um, Heat engine. This is a device that capitalizes on the fact that energy naturally flows from hot to cold and uses some of it to do work. A device that capitalizes on the fact that energy naturally flows from hot to cold and uses some of it to do work. Okay, so it has this same flavor of like, man, the sun is just gives us all this heat energy, like this like radiant energy. If there's a way to like harness that energy and like do something with it, I mean, it's just hitting the ground is like just like man. And so we came up with solar panels. That's solar panels are not heat engines. Just trying to give you the idea. So it's like, man, heat naturally, like energy naturally goes from hot to cold. If there's some way to like harness some of that energy and do something useful with it. Okay. So I'll give you plenty of examples today. All right. So this is a energy model, flow chart, if you will, of a heat engine. So this is your hot reservoir. TH is the temperature of your hot reservoir. And that's going to be measured in kelvins. I'll give you kelvins. Like I'm not going to mess with you to convert stuff. And no mastering over thermo. Okay. This is the temperature of the cold reservoir. Okay, this idea of hot and cold reservoirs, these are like big, massive things, thermally massive, that the temperature of them isn't going to change even if heat is being added or taken away from it. It's the same idea as if you had a 5-gallon bucket of water and you dump that into the ocean. That really didn't change the sea level. Okay, the reservoir there's it's like big. Okay, get rid of that. Now, heat naturally goes out of hot into cold. What a heat engine does is says, hey, you know what? I see this natural flow of energy. Can we redirect some of that and do work, do something useful? Okay, that's what an engine does. Okay, so that heat that's coming out of the hot, that's your QH. Okay, some of that is diverted to doing work. Okay, this is the work done by the engine. And QC, this is the heat. Nope. Let's see. What do I want to say there? That's what I want to say. Leftover heat going into the cold reservoir. It is wasted, sometimes known as wasted or exhausted. Good with that? Okay. So the math behind this, the energy accounting, this is like an energy flow. You have conservation of energy. So you have energy in, has to equal energy out. So energy going in to the engine is QH. What's going out is the work done plus the heat lost. Good with that? Okay. One little detail, ignore positive negative signs for work and heat in heat engine equations. So the stuff that you're doing yesterday, signing positive and negatives, don't employ that when you're using that equation there. And the next one I'm about to show you. Okay. Now, when we talk about heat engines, a very popular term is efficiency. Like, we want an efficient engine. What does that mean? That means we're taking, like, we're given a certain amount of energy going in. If we can make a higher percentage of that to do work, and we're wasting less, we have a more efficient engine. Does that make sense? Okay, so we're looking at this ratio of how much we get out compared to how much we put in. So efficiency is going to be equal to this ratio of the useful energy we get out compared to how much energy we put into it initially. What's the greatest that ratio could be? One, good. Because you can't get out more than you put in. Does that make sense? Okay. Another way to describe this is from the perspective of the heat lost. The difference between these two is going to be your work out. So sometimes efficiency is just expressed like this. Okay. And it's going to be a percentage, like the engine's 35%, or has an efficiency of 35%. So we'll multiply by 100 to make it a percentage. No more. Yep. Yep. Sorry for both of those. Good with that? Okay. So those are the factoids. Talk to your neighbor. Okay. Correct answer is A. That's your source. Okay. Mathematically, it's the sum of these two. That's your input. All right. So one example, first example of a heat engine would be a steam locomotive. So what is in Western movies? What is the car? What is the first car after the engine? The coal car. I don't know, why would we want to bring coal around? Because we burn it. Okay. This burning coal or burning wood, this is our hot reservoir. The temperature of this isn't going to change because we keep putting fuel in there. We maintain that temperature of the hot reservoir. That's our source. Good with that? Okay. Now, if we just burnt wood or burnt coal, where's that heat going to go naturally? Yeah, yes. But more general than up, like that's convection. I totally, yes. Good job. But it's going to go out into the environment. Okay. Our cold reservoir is what? The environment, the air, the atmosphere. Okay. We're not going to change the temperature of the air, that our environment much by burning, like having a campfire. Does that make sense? Okay. So heat naturally goes from hot to cold, but the heat engine says, well, let's do something with some of that energy. Okay. So we're burning coal. This is our hot reservoir. On the train, it's the steam engine. There's got to be water, steam. This front part of the train is the boiler. It holds the water by the fire, heats the water, makes steam. This is becoming pressurized in here. But there's a piston that's movable. What do you think is going to happen to that piston as you heat this water? We're doing positive or negative work here. If our system is the water, positive work. We're expanding. Bum, bum, bum. You good with that? Okay. What does that do for us? Does that make sense? We're doing stuff. We're taking the heat that would have just gone to the environment and we're doing work. Okay? Now, each time it shoots back, after it's expanded, a valve is open and lets that steam out. And then this can fall back down. That steam is let into a condenser that cools that steam down. So that condenser is exhausting that heat to where? What's the cold reservoir? Cold reservoir is the air. You okay with that? It cools that water down. Sorry, it makes the water condense from steam into water and then pumps that water back into the boiler. The water is a closed system, but the energy is not. We're taking heat here, using some of that energy to do work, and then exhausting that out into the atmosphere. You all right with that? Now, we don't see a whole lot of steam engines, but we use them all the time to produce electricity. That's what the coal burning power plants are and nuclear power plants are, which are the vast majority of where we get our electricity from. Okay, we're burning fuel, fossil fuel, or wood, or not wood, just coal. We're burning natural gas or doing nuclear reactions to produce heat to send steam through turbines to spin the wheels. Okay, good with that? So does this example make sense how this model is applied to that? Okay, so this stage here is in the boiler. We're just doing this. We're not changing any volume. The system is the water. Tell your neighbor. Correct answer is, we are no, assuming the volume is not changing. So when we say volume is not changing, what is zero? Work. Correct answer is B. Our environment is hotter than our system. We're adding heat to our system, the system being the water. You good with that? Then we get to the piston part, and we assume it happens rapidly, or do I say that? Oh, there it is. Tell your neighbor. Correct answer is A. Yes, A. Okay, happens rapidly. No heat transfer. It didn't have a chance to. We're doing positive work. Where did that energy come from to do positive work? We're decreasing. It's taking it from the internal energy. We're decreasing internal energy. Good with that? And then lastly, this is a condenser. Assuming no change in volume. No change in volume. Work is zero. The system is hotter than the environment, so we're losing heat, decreasing the temperature. So delta U. So correct answer was C. Good there? Okay. Another example is the engine found in your car. Okay, it's known as a four-stroke engine.
First, intake stroke. The inlet valve is opened, and the fuel-air mixture is drawn in as the piston travels down. Second, compression stroke. The inlet valve is closed, and the piston travels back up the cylinder, compressing the fuel-air mixture.
Okay. What happens when what happens to the temperature inside here when it's being compressed? Increases. You remember the fire plunger yesterday? Okay. Now, in a diesel engine, this gets hot enough to burn the diesel fuel. Okay. But in a regular gasoline engine, it doesn't get hot enough. So,
just before piston reaches the top of its compression stroke, a spark plug emits a spark to combust the fuel-air mixture.
heard of a spark plug? It's the ignition. Okay. Not to detonate, but to combust. It doesn't really explode, but burns quickly.
Third, combustion stroke. The piston is now forced down by the pressure wave of the combustion of the fuel-air mixture.
We're doing positive or negative work here. Positive work. This is what drives you. Does that make sense? That's positive work. This is why we have a heat engine. Like this is why we have an engine right there. Boom. Okay. This is where your gasoline goes. It's what we need gasoline for.
The engine's power is derived from this cycle. Fourth, exhaust stroke. The exhaust valve is opened.
Where's
and
that
the
going?
piston travels back up, expelling the exhaust gases through the exhaust valve.
Out
At the
to
top
the
of the stroke,
atmosphere,
the
a
exhaust
cold,
valve is
cold
closed.
reservoir.
This process is repeated. What had been presented is the cycle of operation of one cylinder of a four-stroke engine. Generally, engines have two or more cylinders acting in concert with each other to produce the engine power.
Okay. If you've heard of this would be an example of an inline four-cylinder engine. A V8 would be 8 cylinders in a V formation. A V6, 6 of them. An inline 6, 6 of them like this. This is a four-cylinder engine. Okay, so this is at the heart of the engine. This is why engines work. Okay, and notice how they're like offset from each other. So there's always one cylinder that gets this power stroke. Good with that? Now, are you familiar with the tachometer, the gauge on your car? Okay, what's the unit on that? Rotations per minute, RPM, times 1,000. Like, look at it. Okay, so let's say you're going down the interstate going 80 miles an hour and you're at 3. Your tachometer says 3. That is 3,000 rotations per minute. Divide that by 60. That is 50 rotations per second. This thing goes up and down 50 times in one Mississippi. You see where gasoline goes. It's the thing. Okay? Does that make sense? Less than that. I just did the three because it's easy math. It's still doing it. You're just not doing any. There's no resistance to that. You're still using gasoline. All right, so check this one out. This is cool. This is like slow motion of a single cylinder, and this is like a lawnmower engine. Okay, spark plug goes off. It's on the right hand side. Boom, power stroke. Pushes up. This is pushing out the exhaust. Sucks in fuel, air. Compression, boom.
So, what gets it going in the car? Because like I'm taking an electric lawnmower, just getting it spinning.
Great question. So a starter, an electric motor, is what is getting this going. Okay. Back in the day, you had to like get in front of your car and like that. Now we have a motor, but that's why when your battery is dead, your car doesn't start because it takes electricity to get the motor to get going. But once it's going, then it's self-sustaining.
Is it the same as like a Polestar motor?
Yes, exactly the same reason. Same thing. They have a starter, but they have diesels engines have a hard time starting in the wintertime because it's cold. So they have what's called glow plugs that heat up the engine block a little bit so that the fuel it will get hot enough to combust in there. But there's still a starter that gets it going. like a motor, electric motor gets it going. Okay? Great questions. Any other questions? Last worksheet, due tomorrow.